Welcome to This Explainer. Today, we're putting on our cloud architect hats, and together, we are going to build and manage a Google Cloud network completely from the ground up. If you're studying for your Associate Cloud Engineer exam, well, you are in exactly the right place. We're going to take all of those complex configurations and routing protocols and translate them into a clear, usable blueprint.
So, picture this high-stakes scenario. It's a Monday morning, traffic to your application is just massively spiking, one of your key virtual machines suddenly restarts, and to top it all off, your CEO just bursts into the room. They've read some terrifying news report over the weekend about a massive company completely crippled by DNS cache poisoning, and they demand to know right now if your infrastructure is safe. Are you ready to fix this? Figuring out these exact issues is exactly what tests your true mettle as a cloud engineer.
To get us out of the woods and prep for the exam, here is our blueprint. We are going to move sequentially through naming the cloud, directing the traffic, securing the infrastructure, managing the real estate, and finally, network service tiers.
Let's kick things off with part 1, naming the cloud, where we set up the public face of the infrastructure.
We start this off by using Cloud DNS. It's a fully managed service, providing highly available, low-latency domain naming services, basically mapping human-readable names to IP addresses. But let's go back to that panicked CEO of ours, who is terrified of DNS spoofing and cache poisoning. How do we secure things? Well, you would immediately recommend implementing DNSSEC. To stop those exact spoofing attacks, your definitive, absolute answer has to be DNSSEC. Standard records just won't cut it for that level of security. DNSSEC is the protocol you need to rely on. Speaking of standard records, though, you literally have to have these memorized for the exam. You really need to know the distinction here. An A record specifies the IPv4 address of a domain, while the AAA record is used specifically for IPv6 addresses. You also need to know that CNAME records store the canonical name of the domain. NS stands for name server, and SOA is your start of authority record. Getting these straight in your head is an absolute must.
Another crucial point is knowing exactly when to use a public versus a private DNS zone. If you want to support queries coming in from the broader open internet, you stand up a public DNS zone. Makes sense, right? But you use a private DNS zone only if you want to accept queries strictly from resources within your own project. And for the command line folks out there, listen up. The exact parameter used to make a DNS zone private is -visibility equals private. It is not -private, it's not -status equals private, it's -visibility. You also need to know about the TTL parameter. TTL stands for time to live, and it dictates exactly how long a DNS record is allowed to exist in a cache before a client is forced to go back and query for fresh information. It has absolutely nothing to do with client timeouts or manual human verification. It simply controls that caching duration. All right, let's test your memory and keep those command line skills sharp. If you were sitting at your terminal right now, what exact command would you type to create a DNS zone? Just take a quick mental guess. Got it? If you guessed gcloud DNS managed zones create, boom, you are perfectly on track. Notice it uses gcloud, not gsutil, because, well, gsutil is reserved strictly for cloud storage, and it clearly specifies the DNS service right before the action. Moving on to part 2, directing the traffic, where we manage the flood of incoming visitors using load balancers. Now that we actually have names mapped to our cloud, we need to handle all those incoming visitors. You absolutely must understand the fundamental difference in how Google Cloud categorizes load balancers. Simply put, is it global or is it regional? Global load balancers, like the global external HTTPS, the SSL proxy, and the TCP proxy, they distribute your traffic across multiple regions worldwide. Regional load balancers, on the other hand, like the internal TCP/UDP or internal HTTPS, are completely confined to working within one single specific region. You don't just pick one of these load balancers at random. You have to map them directly to specific protocols. If you're dealing with standard web traffic, HTTP or HTTPS, that has its own dedicated balancer. Need to terminate SSL or TLS connections globally? You use the SSL proxy. Terminating TCP sessions, TCP proxy. And if you're balancing traffic strictly on private networks that host internal VMs, you're going to turn to the internal TCP/UDP balancer. When you actually sit down in the console to configure something like a TCP proxy load balancer, it's basically a 3-step process. First, you configure the front end, which is where you specify the exact ports that should have their traffic forwarded. Then you set up the forwarding rule, which tells that traffic how to route to your virtual machines.
And finally, on the back end, it's absolutely crucial that you use health checks to monitor the health of those VMs. This ensures the load balancer is only ever sending traffic to instances that are alive and ready to respond.
Okay, here's a classic textbook scenario you might face on the exam. Listen carefully. You're deploying a distributed system. Messages are going to be passed between VMs in the same region using a reliable UDP protocol. You want the load balancer that best fits these exact requirements. Which one are you choosing?
Well, because the traffic is regional, because it's internal between your VMs, and specifically because it relies on the UDP protocol, the internal TCP/UDP load balancer is literally your only correct choice here. Global balancers or SSL proxies just won't support this specific regional UDP setup.
All right, part 3, securing the infrastructure, focusing on private access options.
So the traffic is flowing beautifully now, but we need to lock down the VIP areas of our network. There are 4 specific private access options you really need in your toolkit. Private Google Access is your standard go-to for reaching most Google Cloud services privately. Private Service Access is what you use when connecting with third-party services and some specialized Google services. Private Service Connect specifically uses a VPC endpoint to forward your traffic. And this last one is huge, serverless VPC access. This is exactly what you need to configure if your serverless applications, think Cloud Run, Cloud Functions, or App Engine Standard, need to securely reach your VMs via their private internal IP addresses.
Next up, part 4, managing the real estate, diving into IP addresses and subnets.
Moving down to the foundational level of our cloud architecture, let's actually revisit our panicked CEO's scenario from earlier. Remember how the VM restarted and suddenly users couldn't access the website at all? Why did that happen? Well, it's almost certainly because someone assigned an ephemeral IP address. Ephemeral addresses are fine if you just need to SSH into a VM for a quick little experiment and then shut it down. But they are released and lost forever the very moment a VM stops. If you're hosting a website and need that same IP address to stick around, you absolutely must assign a static IP address. A static address is permanently assigned, stays in your project, survives reboots, and doesn't go anywhere until you explicitly release it. Okay, let's talk about a little bit of subnet math, specifically prefix lengths. Say you create a subnet and you know you need exactly 14 available IP addresses. What prefix length do you use? The magic number is 28. Why? Well, an IPv4 address has 32 bits total. If you use a prefix length of 28, you subtract 28 from 32. That leaves you exactly 4 bits for your device addresses. 2 to the power of 4 is 16. Then you subtract the 2 reserved addresses, one for the network, one for the broadcast, and there you go. You get exactly your 14 usable addresses. Now, if you ever need to increase the size of a subnet, the command is gcloud compute networks subnets expand IP range. But keep this critical exam trick in mind. You can only increase the number of addresses. It is a one-way street. If you allocate a massive subnet with 65,000 addresses and then realize, oops, you only needed 254, you are completely out of luck. There is absolutely no command to reduce or shrink the number of available IP addresses once that subnet is created. Finally, we've arrived at part 5, network service tiers. This is all about choosing how your traffic physically travels. We've reached our last big architectural decision, determining the physical path our network traffic will take. Google Cloud essentially lets you choose between 2 tiers, Premium and Standard. The Standard tier might use the wild west of the public internet to route your traffic between the user and your cloud region. But if you have a strict requirement that all your network traffic must route exclusively over Google's high-performance private network and entirely bypass the public internet, you have to select the Premium tier. Just remember, there's no such thing as a Google-only or non-internet tier in the console. Premium and Standard are the exact terms you'll be tested on. And there we have it. We've built our cloud architecture from configuring public DNS records to terminating SSL sessions on load balancers, all the way down to calculating subnet masks and choosing our network tiers. You now have a complete, structured blueprint of Google Cloud networking. But honestly, deploying a network is only half the battle. Think about it. How are you going to monitor all this when things inevitably go sideways? We'll be tackling cloud operations in a future explainer. Until then, study this blueprint, and you'll be more than ready to totally ace your exam.